Begin today our second part of lesson 4.4 talking about polynomial functions, and we're going to look and analyze different graphs of our polynomial functions. So we're going to look at the first 6 special cases here. First one being a constant function. So when we graph a constant function, maybe for an example, f of x is equal to 3. When we graph that, what is happening here is that our y value, no matter what x gives us, is constantly on 3. So it gives us that horizontal line, whether it's 3 or at -4 or at -2, it remains constant the entire time. Now, for our linear function, maybe an example of a linear function is simply x plus 3, where our y-intercept is 3 with a slope of 1, rising and running. You can see that as soon as I add slope into my function that I get more of a diagonal line, making it linear. Now if I talk about how many zeros I could have on a function, with a linear function I could have at most 1 real zero. And that is because my degree here is at 1. Now we're going to link some kind of relationship between the degree and how many real zeros that we actually can have. So a quadratic function. So we've studied quadratic functions for quite a while this year. So I'm just going to give you a generic one, ax squared plus bx plus c. And we know that we can put that in to vertex form, or we can graph it using the axis of symmetry. But either way, when we graph a quadratic function, we get that parabolic shape to where the degree of our quadratic function is 2, and you can see that we could have at most 2 real zeros. Now in studying quadratics, we know that we might have just 1 real zero or no real zeros, but the most that we could have is 2. Now we're going to start to investigate what a cubic function looks like. So a cubic function would be a generic function of a cubic function would have a 3rd degree. But a cubic function could look something similar to this. Now this could be a complicated version of a cubic function, or it could look as simple as this. Now when I talk about a cubic function is going to have a degree of 3, and it could have as many as 3 real zeros attached to it when we look at graphing that. Or it could have just 1 real zero depending on where that axis hit. But the most it could have would be the amount in the degree that it matches the real zeros. For a quartic function, we start to look at a degree of 4. So that would be your 4th degree polynomial, taking an x to the 4th power and combining it with other x values. Now when we have a quartic function, our graph tends to look something like this. Now that would be, again, the most complicated version of a quartic function. It could look as simple as this, as a parabola. But the most complicated version of a quartic function is that it has 4 real zeros that matches the degree of the polynomial. And our last one that we're going to talk about today is a quintic. And a quintic is a polynomial function of degree 5. And its most complicated version, where it crosses the x-axis 5 times, 1, 2, crosses 3, crosses 4, crosses 5 times to give us 5 real zeros, 3, 4, 5 real zeros. Now some things that I want you to notice when you're looking at these polynomial functions, or look at the difference in where the ends of the graph are going. Because in your linear function, in your cubic function, and in your quintic function, The ends of the graph are going in opposite directions. Notice that those are all of your odd degree. So you have a degree of 1, a degree of 3, and a degree of 5. They end in opposite directions. But when we look at the even degree function, your quadratic with a degree of 2, a quartic with a degree of 4, they end in the same direction. So that takes us into talking about what the end behavior of polynomials actually looks like. So with the end behavior, we're looking at two different type functions. Either the function is going to be an even function or it will be an odd function. Now we talked yesterday about the leading coefficient. The leading coefficient is going to have a lot to do with where the graph ends. So if you're talking about an even function, so that's your quadratics, that's your quartic functions to the 4th degree, to the 6th degree, to the 8th degree. If your leading coefficient is positive, leading coefficient, or if it is negative, it's going to look very differently. And you'll remember this from talking about quadratics and graphing those parabolas. If it is an even function, it means it's going to end in the same direction. We might not know what it does in the middle, but if it has a positive leading coefficient, let me write that here, that this is the leading coefficient. If it has a positive leading coefficient, then it ends in the same direction. They both end up. Again, we're not sure what it does in the middle, but we know that the ends of the graph end up. If it is an even function and the leading coefficient is negative, then the ends of that graph are going to end down in both directions. Notice that they have to go in the same direction. All right, for an odd function, they're going to go in opposite directions. Now, if our leading coefficient is positive, for an odd function, it's going to always increase. So it's going to start low and end high. However, if that leading coefficient is negative, it's going to be a decreasing function where it starts high and ends low. So how do we write those end behaviors? So we did this earlier in the year, but we're going to look at it again. So here's a polynomial function. Looks like a really wide parabola, but both of the ends of the graph are moving downward. So we write this so that I show the left-right movement as far as matching with the positive negative of the y value movement. So I'm going to write this as x goes to infinity to the right. That's what that means. Our function is going down. So our function is going to negative infinity. So it's where it's pointing. Now if I write it over here as x goes to negative infinity to the left, then my function is approaching negative infinity as well. Now what I want you to notice here is that when our ends are going in the same direction, that must mean that this is an even function. And because they're both pointing down, that must mean that our leading coefficient, I don't know exactly what my leading coefficient is, but I know that it has to be a negative value. Okay, so just by looking at the graph, I know that I'm going to have an even function. So it could be a 2nd degree, it could be a 4th degree, it could be a 6th degree. And I know that my leading coefficient is negative because the ends are going down. Let's look at another one like this. So, I think I forgot to state the real number of zeros. So this one, in fact, could have 2 real zeros, it could have 4 real zeros, it could have 6 real zeros, but it actually has none because it never crosses the x-axis. So this one is going to have no real zeros. So we described the end behavior by using this table here. We determined that it was an even function with a negative leading coefficient and it has no real zeros. So let's look at our next one. For our next one, we can see that our ends are going in opposite directions. Now, if I describe the end behavior, I can say as x moves to negative infinity, the function goes to, I should write it underneath to make it a little bit easier to see. As x goes to the left, the function is moving down to negative infinity. But as x moves to the right towards positive infinity, our function is moving to positive infinity as well. So when you see that these two ends of the graph are going in opposite directions, that means that this has to be an odd function. Now, because it is constantly increasing and it starts low and ends high, that means that my leading coefficient is positive. If it were a decreasing function, then my leading coefficient would be negative. Now, if I look at this and I want to find how many real zeros, I need to see how many times it crosses the x-axis. And in this graph, it's only going to cross one time, so it's going to have one real zero. Now, that's looking at that function with a graph, graphically. What if I'm just giving you the polynomial function? Can you describe the end behavior? So what I see here is an odd function, and the leading coefficient is negative. So that means as x moves to negative infinity, my function is going to move, if it's a leading coefficient that's negative and it's odd, that has to go in opposite directions. So as x goes to the left, my function's going to go to positive infinity. As x moves to positive infinity to the right, my graph is going to go down to negative infinity. So what you can see here is that it's ending in opposite directions, starting high, ending low. That's how you calculate the end behavior. So this is the shape of this graph. Now, how many mins and maxes we have in between, we'll decide that later. Right now, we just want to know what the ends of our graph is doing or are doing. Let's look at our g function here. So our g function has a power of 4, a degree of 4. So that means it's an even degreed function, and it has a leading coefficient of positive 3. So my leading coefficient is positive. So because that degree is even, it means it's going to end in the same direction. And because that leading coefficient's positive, they're both going to end up. Now, I don't know what it does in the middle, but I know they're both going to end up. So as x moves to negative infinity, the function is going to move to positive infinity. As x moves to positive infinity, the function is going to move to positive infinity. Remember, this just means left and up and right and up, so that they're ending in the same place. So when completing this lesson, we should be able to decide how many real zeros we have by looking at a function, how to determine what the leading coefficient is it positive or negative, and the degree of the function, and what all of that does to the ends of our graph. Look on Google Classroom for your assignment.